It's at CNRS and University of Lille, and take it away, Emilie.
Can you all hear me? Do you see my screen?
Yes.
Okay, perfect. Thanks, Shipra, and thanks for having me at this workshop. So today I will present some work we did this spring with a bunch of nice colleagues from INRIA, Pierre Ménard, Omar Darwish Dominguez, Anders Johnson, who was doing his sabbatical with us, Edouard Laurent, and Michal Valko, who is in DeepMind. So this work will be about two pure exploration problems in the context of reinforcement learning that I'll try to describe shortly. So first, a quick recap. So in the RL setup, the common denominator is always an agent interacting with an environment by choosing action, observing rewards, and also transition to a next state. However, the agent can have different goals in mind. And indeed, there are several performance measures that have been considered in the theoretical RL literature. So first, you could imagine that your agent is acting out there in the wild, and so you want it to adopt quickly the good behavior you're trying to incentivizing, which you can measure by the total reward that your agent gets while interacting with the environment. So this is related to the notion of regret that we try to minimize in some part of the literature. Another related formalization of a similar objective is to try to count the number of steps in which your agent behave epsilon suboptimally. So this is what is done in the PAC-MDP formalism, which is also related to having a lot of reward, I would say. And so in this PAC-MDP framework, there have been some sample complexity guarantee given. So in this talk, we will consider the sample complexity of different exploration problems in MDP, in which we forget the need to maximize reward. For example, we could let our agent do as many mistakes as he wants, but at the end of the day, he has to tell us what he should have done, what is a good policy to adopt in the current environment. And so we will consider two variants of this exploration problem. So in the first, we will give the agent the reward function that is important to him, and he will try to learn a good policy with respect to this reward function. And then we will consider a more robust exploration problem in which we ask the agent to have a good feeling about the environment so that he's able to find the optimal policy, whatever reward function we give him later. So those are a high-level description of these two pure exploration problems that we will study in this talk. So in what context will we study them? So what is our model for the environment? So here I will have many people disappointed, but I will just choose the simplest possible MDP model that is an episodic Markov decision process, meaning that we always interact with the environment in H time step, successive time step, where the horizon H is known in advance. And hence our MDP is parameterized by the states and action space that are assumed to be finite in this talk, and also by the set of all transition probability. So here, PHS prime SA is the probability to end up in S prime, given that we choose action A in state S, in step H of the episodes. So if we know all the probability, we know perfectly the dynamics of our MDP. And then the reward function assigns a reward for choosing action A in state S at step H. So based on this MDP, we are interested in learning good policies. So policy is simply a mapping from state to action. And the quality of a policy is, as usual, measured by its value, which is a cumulated sum of rewards you get from this state, applying the policy, and of course, transitioning under your transition probabilities. Okay, and so we know well from the theory of MDP that there exists an optimal policy whose value is larger than that of any other policy for any state and in any time step. So here I highlight the fact that rewards will play an important part in this talk, as I already mentioned. Therefore, I will index my value by the rewards. And also the P star R is the optimal policy in the MDP with transition kernel P and reward R. So the transition kernel, of course, is important too, but it will remain implicit, at least in my notation. So last thing I have to mention, I will, as often, also work with the Q value because it's convenient. So it's like the value, except you start by taking a particular action A in state S. And the last thing I need to highlight for experts is that here I consider the general setting of step-dependent transition and reward. Sometimes have the paper consider rather static, so this P and R do not depend on H. I just mentioned that for people who might know what to expect in terms of scaling in the horizon. And so if you see an extra H, it's because I'm considering the step-dependent model. Okay, so this is for the background. Now I'm ready to present these two, to formalize mathematically these two problems that I'm going to study. First, I need to explain to you what is an algorithm for me. So there are different data collection process that one can consider in RL. So in this talk, we will constrain the agent to use a forward model, that is to sample trajectories, episodes, in a sequence of successive states, as opposed to some paper who consider the possibility to have a generative model, that is to go in any state, see what happens in whatever order. So in this interaction framework, the agent will always use for each episode T an exploration policy that I will denote by pi T. And this exploration policy will be used to generate an episode that is a sequence of state and action, where the action is taken according to the policy, and the next state is sampled according to the unknown transition. So in this talk, the agent will also have the possibility to stop exploration at some point and to output a prediction. And the prediction will be the difference between the two frameworks will differ by the prediction that is made. But what is common is that these three components, exploration policy, stopping rule, and prediction, can all three be data dependent. And yeah, for simplicity, I will consider that we always start in the same states, all the episodes, but it can be easily extended to a distribution over first states. Okay, so the first more well-known framework is that of best policy identification that I will often call a BPI, that can be traced back to a paper by Fischer in 1994. So this paper will have importance later in this talk, so remember it. This problem was described in this paper in a discounted setting, but with a restart button. And in the end, it was really using episodes. So it's very much equivalent to our episodic setting. And in this setting, the agent knows the reward function, and you want to learn the optimal policy in an MDP with this reward function. So then an algorithm for BPI can have an exploration policy that depends on the data observed in the past episode, and also on the reward function R. The stopping rule will be a stopping time with respect to the accumulated data that can also depend on R. And finally, the prediction is a policy that also depends on the data you have until stopping and the reward function R. And what we want is to build an algorithm that is epsilon delta probability approximately correct, PAC, in the sense that with probability larger than 1 minus delta, the predicted policy has its value that is within epsilon of the value of the optimal policy. And we want to achieve this while having a small sample complexity tau, that is using as few episodes of exploration as possible. The reward-free exploration framework, RF-E, that we consider now, is a bit more challenging and was formalized at ICML this year by Shijin and co-authors. The idea is that we want to be able to learn the optimal policy for any reward function. And for this, we will use an exploration strategy, of course, that cannot be tailored to any reward in particular. So we just assume that the agent doesn't know what reward the optimize is for. However, he still uses an exploration policy that can be data dependent, a stopping rule, and then its prediction will be this time a transition kernel. So an estimate of all the transition probabilities in this MDP the agent was interacting with. And based on this predicted transition kernel p hat, actually it is possible to compute the optimal policy in the empirical MDP with transition p hat and with reward function R. Just using backward induction in our tabular setting, this is super easy. And so we will be a bit more demanding for an epsilon delta pack algorithm for reward-free exploration. We will ask that this time, still with probability larger than 1 minus delta, for any reward function, if you take the optimal policy associated to a particular reward that is estimated from your kernel, you are epsilon away at most from the optimal policy for this particular reward. And of course, we still want to do that with a small sample complexity, small number of exploration episodes. So a possible motivation for this framework is that, like, if you design, I don't know, you want your robot to do something, you don't know at first what good reward function will make it do the something you have in mind. So you will try one reward function, try to find an optimal policy. And then if you realize it's not good, maybe you will change your reward function. And so each time in this trial and error process, you would need to redo the full exploration in order to find a policy. In reward-free exploration, actually, you do a bit more robust exploration to be able later on to plan for any reward. So this is one of the motivations that was given by in the Shijin paper that I think is very relevant. And now I'm going to present a very simple algorithm actually to solve this seemingly challenging reward-free exploration problem. So this algorithm will be a model-based algorithm. So thanks to Chiara's talk, you already know what that is. So it is an algorithm that will estimate the model, so the underlying transition probabilities. And in the tabular setting that we consider, we will consider the simplest possible estimate of the transition probabilities that are based on the number of visits in each state action pair. So this notation is particularly important. NHTSA is the number of times we have been in state action pair SA in step H of the episode before time t, before the t episode. And then the transition, the estimated transition, you just count when you were in SA, how much time did you end up in each of the different states. Okay, so based on this empirical transition vector, so p hat t, the set of all these transitions, again, you can define the value in the associated empirical MDP and the Q values that I will always denote by V hat and Q hat respectively. And now, actually, a central observation to have an idea to design an algorithm for this problem is that a sufficient condition to be epsilon delta pack for reward-free exploration is to have an accurate estimation of the value function for all rewards and all policy. Meaning that based on my current p hat t, if I construct the estimated value v hat t, I want it to be close to the true value of this policy. And I want this for all policy and all reward. So how do we achieve this? So we use an idea that is very well spread in model-based RL. So the problem is here we have a quantity v1 pi that we do not have access to because it depends on the true transition. So we will try to build upper confidence bound on this error. So for convenience, I will look at the error between the estimated Q value and the true Q value. And we will build upper confidence bounds that are fully data dependent, meaning that can really be computed at a given episode t. And the very nice thing is that this upper bound will be independent on pi and r, meaning that then we can devise an algorithm that is greedy with respect to this upper bound, so that somehow reduce the error as fast as possible. And so when these upper bound are below epsilon/2, then we know that this sufficient condition is satisfied, and we know that the algorithm is epsilon delta pi. So how do we build the upper bound? So again, it's a very standard idea. And so these upper bounds that I denote by E bar are defined inductively. So here you have a relationship between E bar at step h and E bar at step h+1. And we see that they feature something that we would call an exploration bonus. So a quantity that scale in a square root of 1 over the number of visits. And here we have an extra little thing, a threshold function that is to be thought as a log n, basically. So where does this come from? Actually, just like in UCRL, this construction rely on considering a confidence region for the transition probabilities. And indeed, what we can show is that on this event E, in which for every step and state action, the true unknown transition probability is close to the empirical transition probability p hat t. And here you see the closeness is precisely measured with this beta over n. So on this event E that we will be able to show easily to make it of probability 1 minus delta if we need, on this event for every pi and every r, we can easily show that this upper bound is larger than the error. And when I say easily, it's really this one slide. It is just a consequence of the Bellman equation applied to the empirical MDP and to the true MDP. And we see that when we are interested in the error, which is the difference of these two quantities, you see that the rewards naturally cancel out. So this is the reason why the upper bound will not depend on the reward. And then rewriting a bit things, we managed to upper bound the error at step h by the L1 norm between the true probability transitions and the estimated ones. And on our events, we know, thanks to Pinsker inequality, that this will be upper bounded by the things that appears in the bound, so the square root of beta over n, basically. And then the other term here is the error at step h+1. Here we still have a dependency in pi, but here by taking the maximum over all possible action, you can get rid of it. And then using induction, you manage to upper bound this by the upper bound at step h+1. So this is a simple justification of this formula. And once that we have our upper confidence bound, as I told you, the exploration policy of this reward-free UCRL algorithm will be the greedy policy with respect to this quantity. And the stopping rule is, as we expect, the moment where the error in step 1 is smaller than epsilon/2. Because as I told you, when it means the error is smaller than epsilon/2, which means that the policy will be correct, will be within epsilon of the true optimal policy for any reward. Okay, and so my prediction is my current transition kernel P. So this algorithm, actually, we came up with it by reading this paper by Fischer, who was proposing something very similar, so still in this discounted setting. And we realized, so it was aimed at an algorithm for this other, simpler, best policy identification objective. However, we realized that the algorithm is not depending on the reward function in any way. So that's why we thought it should be a good candidate for this more challenging reward-free exploration problem. So indeed, we managed to control its sample complexity for the reward-free exploration problem. So by choosing a threshold of order log 1 over delta plus s log n, we can prove that the resulting algorithm is epsilon delta pack. And also we can give a high probability upper bound on its sample complexity that has the following scaling in the MDP parameter. So it's in H4SA divided by epsilon square log 1 over delta plus S. And so this upper bound we managed to give is improving the upper bound given by Shijin. So to see the improvement, if you, for example, if you don't care about delta and you look at the scaling in epsilon, this is a term in this bound, and we get an H4, so we improve the dependency in H by power 1. And then we can also note that the dependency in delta is greatly improved over there. So besides the improved sample complexity, what is interesting conceptually is that the two approaches are really completely different. So I don't have time to go into detail about Shijin's approach, but they are leaning on some regret minimizing algorithm. And so we think that RF-UCRL is a natural adaptive approach to reward-free exploration, leveraging this idea of uniformly reducing estimation error for any policy. And another plus is that it has a simple sample complexity analysis. So I managed to make it in one slide, but still in the interest of time, I think I have to skip it. So if you want more detail offline, I can give some. But I want to go back actually to the initial motivation of the algorithm that we draw inspiration from. So this algorithm by Fichter was aimed at solving the best policy identification problem. So a natural question is, okay, so how good is this reward-free exploration, this reward-free UCRL algorithm for the initial objective it was proposed for? So indeed, RF-UCRL can be used for best policy identification. All you have to change is the prediction rule. Instead of predicting a full transition kernel as required in RFE, we just output p hat, which is the optimal policy in the empirical MDP associated to this kernel, and we inherit the same sample complexity guarantees as RF-UCRL. So how good is this? So to answer this kind of question, it is common to look at what the lower bound says. And here I'm advertising a recent results that we did with Omar and Pierre and Michal. Actually, so this might be a folklore knowledge, but we give a very clean proof of this lower bound, saying that for any epsilon delta pack algorithm for BPI, there exists an MDP with stage-dependent transition for which the sample complexity has this H3 scale. So we see that indeed there is room for improvement because we have an H4 and there is also this additional S. I did not really need to look to show you the lower bound to know that there is room for improvement because as I already mentioned, RF-UCRL doesn't use the reward. So if you are given the reward and want an optimal policy for this particular reward, you should design an algorithm that leverages the reward. And actually, there are already some algorithms out there in the literature. Typically, algorithms that leverage some regret minimizing algorithm. So I present here a conversion from regret minimization to best policy identification that was proposed in the optimistic Q-learning paper of Shijin and co-author in 2018. So if we take the UCBVI algorithm of Hazard et al. That attains the minimax optimal regret. So we know if we have an algorithm that has this type of bound on the accumulated regret, it means that because the regret is small, the policies, not all the policy used by the algorithm can be bad. So there must exist one policy at some point that was good. And so the idea of this conversion is to choose in advance some deterministic stopping time, well calibrating depending on this regret bound that we have, and then just output as a prediction rule one of the previously used policy chosen uniformly at random. And so we can prove that this algorithm is indeed epsilon delta pack. And what is cool is that it has this optimal, here we have an H cube. So it has the optimal scaling prescribed by the lower bound, except if you look at the dependency in delta. Here you have a 1 over delta square instead of a log 1 over delta, which is pretty bad. So we can come up with a smarter conversion that would get you, for example, log 1 over delta square. But I didn't succeed in making this static conversion scale to log 1 over delta. So I will just present you what we propose to do instead. So as before, we propose to be more adaptive, meaning we still can rely on a regret minimizing algorithm, but we will assign to a regret minimizing algorithm a data-dependent stopping rule that would tell us, okay, now I can stop, and this is my my optimal policy, and not choose a policy at random in the past. So we do that with a variant of a UCRL algorithm that builds some upper and lower confidence band on the Q values of the optimal value and optimal Q value. The exploration policy of this UCRL algorithm is to be greedy with respect to the upper confidence band on the Q value. And then the stopping rule that we've proposed is to stop when the size of the confidence interval of the value in step 1 is smaller than epsilon. And with this stopping rule, you can show that if you predict the greedy policy with respect to the lower confidence band, then you are indeed epsilon delta pack. So we managed to, and here, yeah, just note that here the algorithm depends on R everywhere, because to build the confidence intervals on the value, you will use the knowledge of this particular reward that you have in mind. So what we proved for BPI-UCRL is actually basically the same thing as RF-UCRL, because the nice thing is that the two proofs are very similar. However, it means that we cannot show any improvement for this algorithm from the theoretical bound. And this is why we ran a few experiments to see if indeed using the reward can be a bit smarter than doing this reward-free UCRL. And the answer is indeed it can help. So we measure here the empirical sample complexity for different values of epsilon obtained on a toy problem like a double chain MDP. And we see that there is really an order of magnitude different. Here the y-axis have the same scale between RFE and BPI-UCRL. So indeed, the algorithm is better in practice, even if the theory failed to prove it so far. Okay, so to summarize, so the purpose of this talk was to investigate the sample complexity of these two related problems of best policy identification and reward-free exploration. So for best policy identification, so far our current approach are not exactly attaining the lower bound because of an extra factor H and an extra factor S. And for reward-free exploration, actually, as pointed out in Shijin's work, the factor S has to be there. They give a lower bound in the small epsilon setting. However, there is also this little room for improvement in H. And so I'm just mentioning here a follow-up work in which we managed to shave off this extra H factor by using some more sophisticated Bernstein stuff. But I chose not to present this because the algorithms are a bit harder to describe. So you can look at this nice preprint. And especially, it's really non-trivial to apply these hazard techniques for reward-free setting, because they rely on working with empirical variance of values, and values depend on reward. So when you do not know what the reward is, it's some more work has to be done. So if you are curious about this and you're geeky about shooting exactly the lower bound, you can have a look at this nice work. What I also want to point out as future work is that when you see this real gap between RFE and BPI, you can wonder whether we are looking at the right thing for BPI, because here I presented worst case bounds, but I think it's natural to try to go for problem dependence guarantees for best policy identification, and I don't know what they look like when you do a BPI based on trajectories. So yeah, that's it. And I conclude with a few references.
Thank you, Emilie. Can you guys hear me now?
Yeah, it is.
So I'd like to ask Mandy now to join to share her screen.